Now that we have a good grasp as to what solutions are, how they're made, how to determine whether something will be soluble or not, and even how to read the graphs to determine the change of solubility, which is dependent on temperature, what we need to do now is basically be able to quantify just how saturated or unsaturated a solution is, and we do that by determining its concentration. The best way to do that mathematically is something that we call molarity. Molarity is simply calculated as the moles of the solute divided by the liters of the solvent, or the total solution for that matter. So what we have here again is the equation that you see right here. This is what I just described. If we need to solve for moles, again, there's another way that we can rearrange it like that, but I'll show you guys that here in a moment. But the main equation again is this one right here. So for number one, it says what is the molarity? So we're looking for the molarity of a 355 milliliter soda that contains 40 grams of glucose. Now there's two problems with this. We're looking for molarity, and that's going to equal moles. Well, I don't have moles, but I do have my grams of glucose. So what I need to do first is I need to convert my 40 grams of C6H12O6, which is glucose. Again, I'm going to put grams of glucose down here and moles up above it. For every 1 mole, it would equal the mass from the periodic table called molar mass. So I'm going to add up the mass of carbon times 6, plus I'm going to add the mass of hydrogen times 12, and I'm going to add up the mass of oxygen times 6, and the molar mass of glucose comes out to be 180.156. Okay. So I'm going to take my 40, I'm going to divide by that answer, and that would come out to be 0.222 moles of glucose. So now that I have my moles, I'm going to go ahead and put 0.222 moles, and I need to divide that by liters, not milliliters, but liters. You guys know that if I take 355 milliliters, put milliliters down here and liters up here. For every 1 liter, it's 1,000 milliliters. So I would take 355 divided by 1,000, or basically move my decimal 2 spots to the left, 3 spots to the left. That is, I did not calculate that right. Sorry. Yep. So it'd be 0.355. Okay. So what I get is 0.222 divided by 0.355, and my molarity, which is a capital M, is 0.625 molar. So it's called molarity, but when I say the answer, it would be 0.625 molar. We don't say 0.625 molarity. That just sounds kind of funny. Molarity is the calculation. Molarity is a concentration, but the answer is molar. All right, number 2, determine the mass of a solute needed to make 2.5 liters of a 1.75 molar solution of barium nitrate. Okay, so we have our molarity, which is 1.75 molar, equals, we need some number of moles divided by 2.5 liters. Okay, so of course what we're going to do algebraically is I'm going to multiply this side by 2.50 liters. Do the same thing over here. I'm just showing you guys the long way. And those of you who know algebra, you know what I'm doing. That's going to cancel that out. Therefore, x is going to equal the left side multiplied together. So 2.5 times 1.75 equals 4.375 moles. Now that I know my moles from my molarity in that particular volume, the question is not asking for moles, the question is asking for grams. So I need to convert into grams. I'm going to put moles down here and grams up above it. For every 1 mole, it would equal the mass of this barium nitrate is BaNO3, 2, and nitrate, of course, has a charge of 1. So now I need to find the mass of barium nitrate. So this is going to be fun. So the mass of barium is 137.328 plus the mass of 2 nitrogens, 14.007 times 2. I'm going to add the mass of oxygen times 6. And the mass of barium nitrate is going to be 261.336. Cancels. And finally, so I have 4.375 times my previous answer gives me 1,143.345 grams of barium nitrate. Okay, so that one again, not too difficult. We just used this simple molarity calculation. The only curveball they threw at us is they didn't want us to solve for moles, which was the easy part. They wanted us to go all the way into grams. Now for number 3, it says calculate the volume of water. So we're looking for the liters of water needed to make a 0.125 molar solution of 0.367 moles. Now, I'm going to go ahead and put this in here, but I'm going to show you guys this is going to be a little bit weird. So we have this, we have our unknown number of moles. Oh, excuse me, I got that backwards. We have our moles up here, 3.67 moles over our unknown liters. Now, I'm going to show you guys, let me simplify this. Molarity equals moles over X, our liters, okay? So algebraically, the way we'd want to do this is we would want to multiply both sides by X, okay? What that does is that cancels that out. Again, I'm just showing you guys an algebra real quick. So now that we have this, what I need to do now is to get X all by itself, I'm going to divide both sides by molarity. Okay, that will cancel that out. So basically what I just did is I swapped places. Again, notice I had molarity on the left and X on the bottom. Now I have X on the left, molarity on the bottom. So ultimately, whenever you see this algebraically, you just switch the bottom X with what's on the left side. Notice moles didn't move at all. The numerator on the right side is completely left alone. Basically, I took the number all by itself on the left and the denominator, and they switch. Algebraically, that's a shortcut. All I have to do now is switch them. But that is the reason why, mathematically speaking. I just wanted you guys to see that before I do a shortcut and I confuse anybody. So this would be equal to X equals 0.367 moles divided by my molarity, 0.125 molar. Those are the same thing, okay? So I'm just going to make this quote real simple, 0.367 divided by 0.125. That gives me a volume of 2.936 liters. There we go. So again, that looked kind of difficult algebraically speaking. The math is really quite simple. Again, if you have a number by itself on one side and a denominator that is the missing variable, your X, all you have to do is swap them. The numerator on the right side isn't even affected in any way. So that was quite, well, easier than it looked. Number 4, calculate the molarity of a silver nitrate solution that contains 15.5 grams of silver nitrate at 250 milliliters. Okay, so this one's a lot like number 1. Again, all we need to do is calculate the molarity. That's really simple, but we need to get our grams into moles, and we need to get our milliliters into liters. Okay, so I'm going to go ahead and do my gram to mole conversion first. So I have 15.5 grams of silver nitrate, which is AgNO3. All right, then I'm going to move my grams down here and my moles up here. So for every 1 mole, I would have the molar mass of silver nitrate. So the mass of silver is 107.868. I'm going to add that to 1 nitrogen, 14.007, and I'm going to add that to 3 oxygens, 15.999 times 3. And my mass of silver nitrate is 169.872. So I'm going to go ahead and take 15.5, divide that by my previous answer, and my moles is going to be 0.091 moles. And then my liters, remember, basically all I have to do to go from milliliter to liter is move the decimal spot 3 spots. So that's going to become 0.250 liters. Okay, so I'm going to take 0.091 divided by 0.250, and my molarity comes out to be 0.364 molar. All right, guys, there we go. That's how you calculate the molarity of a solution, which again, to put that in another way, is the numerical concentration, the quantified concentration of how strong or how dilute, how concentrated is a solution. And again, we just do that by calculating the amount of solute, the moles of solute, which is then dissolved, excuse me, into the entire solution. The stronger, the more concentrated it is, there would be more moles in that volume. Therefore, your molarity would be a higher value. If you have a very dilute solution, then you don't have a lot of moles of your solute. Therefore, your molarity would be a much lower number. So I would say that number 1 and number 4, being both less than 1, are pretty dilute solutions, okay? As always, guys, thank you very much for watching.